Right. In this, we're going to look at electron configurations. We're going to first of all look at electron configurations the way that you might remember them from your past models of the atom, which worked up to number 20, so the Bohr model. Then we're going to look at the quantum mechanic model and how that is different and how it's similar. So we're going to put anything that's in common in the middle between these two models. I must stress that both only models. We don't actually really see atoms, especially not at this level. So we have to make inferences from observations that we make. So just for the purpose of today, I'm not going to go through the evidence that gives us these. That will become more obvious when I start talking about ionisation energy and things like that. All right? So just bear with me as this is just a whole lot of facts, really, rather than the justifications for those. Okay, so let's quickly first of all go through what we currently understand about electrons and how they're arranged in an atom, or in which part of the atoms. What do we know so far about electrons? We covered some of this last time.
Energy levels.
Energy levels. Okay, so they're found in different energy levels, and we'll explore that in a moment. I'm going to put that in the middle, because that's true for both.
They have a configuration of 2, 8, and however many other.
So if we just go to how we currently know it, 2, 8, 8. Okay, so arranged in 2, 8, 8, and so on. We don't really know about the so on because we never got beyond 20, so we got to 2, 8, 8, 2, and then stopped. Okay, that's fine. That's not going to be true for this model. Okay, that's not going to be true. Loosely true, but not enough to put in the middle. Okay, but energy levels is completely correct. What do we know about how those energy levels are arranged? In other words, where do the electrons fill up from?
Inside out.
Good, from the inside out. So they start nearest the nucleus, and then once that energy level is full, you add some to the next, and so on. Okay, so they fill from the nucleus away. Okay, I'm not going to put that up. That's just a bit of information and understanding about energy levels. Good, and that explains our 2, 8, 8. 2, then when we get to our third electron, it goes in the next energy level, and so on. Cool. What else do we know about just how electrons are arranged, or how they move, or whatever? How do we draw them in the Bohr model? Sorry? They're in pairs. Okay, so they pair up quite often. That's actually true in both. Okay, the reason is different for these two, but it's something they have in common. Tend to draw them in pairs. That's very good. What else? How did you draw them in a Bohr model? How do we draw those?
Circles.
In circles. Okay, so they did orbits like a planet around the sun, didn't they? So they're going just in a circular orbit. And then we told you it's really a spherical orbit, which is not quite right either. What it did is it gave you a space where those electrons have the highest probability of being found. That's getting more to that model. But we drew them in the Bohr model completely incorrectly as circular orbits. Okay? And I mean, that's grossly oversimplifying how it works. But it worked really well for the first 20 elements. Okay? So that's why you were taught that. Is there anything else about electrons that maybe is important to know?
They have a charge.
The negative charge?
Yeah.
Cool. Okay, I'm not going to put that up because it was in our last one. The number of them is determined by, and an atom is determined by
The atomic number.
the atomic number. Which ones are removed if we want to make a cation?
The outside valence.
Good. So the outermost removed first to make a cation. Okay. So the outermost electrons are called what starting with V?
Valence.
The valence electrons. This is true in both. And this becomes really important when we look at the transition metals because of the way they're arranged. I'll get to that later. Okay. So that's something that's in common and quite important. Okay. What's different is the stuff we're going to be taught next. And this is where we're going to go on this side here. In reality, well, not truly reality, but in this model, the electrons are still arranged in energy levels. Those energy levels contain different orbits, which are not circular. They're not even all spherical. One type is, but not all of them are. So energy levels are split up into orbits. or orbitals. Okay. Now, the reason this pairing up thing is so important is that's really important for the orbitals. Every orbital can take an even number of electrons. And it depends on what orbital it is, which is actually a different shape, as to how many each orbital can take. Now, each orbital is broken up into suborbitals, but I'm not going to go into that idea too much. But it is useful to know a little bit about. Okay. The names of these orbitals are S, P, and D. Now, I'm not going to talk about the F orbital because that's those ones at the bottom, CE through to LU, TH through to, I think it's LR from memory. So we're not going to cover the F orbital this year, so I'm not going to mention it. Looking at these outermost electrons being the valence ones, I can sort of link these two ideas. If I quickly sketch a periodic table, and you'll see that I'll draw it quite a simplistic way. Okay, I've kind of broken it up into blocks. The valence electrons in, sorry, I've got to take helium off as well. The valence electrons in this block are all in the s orbital, and so is helium. Okay, not that we really have valence electrons for a noble gas, but if we think that the outermost electrons are in the s orbital in these ones here. If I go into here, the outermost ones are going to be in a thing called the p orbital. And in here, sorry, it's not outermost, but these ones contain electrons in another special orbital called a d orbital. And then these ones contain the f ones. Right, now what we need to be able to do is, first of all, our most simple skill is to be able to write electron configurations to show how this works. So instead of 288, our way of writing it is something like this. If I do exactly the same as what I've got there, 288, it would be written like this. 1s2. That means 2 electrons in an s orbital in the first energy level. 2s2. 2 electrons in the s orbital in the second energy level. We're starting up at 2,2. Then it goes 2p6. 6 electrons in the p orbital in the second energy level. So we're up to 2 and 8. And then it just follows the same pattern. 3s2, 3p6. This would be 288 using what's called SPD notation or SPDF notation. And this is way more useful than 288 now, because it will help us explain a whole lot more properties that you were told in previous years, well, don't worry about that, you'll learn about that in level 3. You're about to learn about that. Okay? Or don't worry about that, you don't need to know that, because maybe you were at that stage considered to only be a merit student, not an excellent student. Yeah, you're going to learn about it now. Okay? Well, not today, but you're going to learn about it in this unit. So, something's changed, and we need to be able to do this for the first 36 elements. So here's the other change. Over here, you only had to go up to the first 20 elements, which is calcium. You had to be able to do electron configurations for them. Okay? Now, you need to be able to do the first 36, which means going up to, and I'm sorry, I should know this off by heart, krypton. Are we krypton? Am I that far down?
Yeah.
Yes. Okay, so you need to be able to do it for those. And that's something I want to go through today, is how to write these electron configurations. There are some exceptions to the rules, a thing called Hundt's rule that I'll have to introduce. Okay? And that's where things can get a little bit confusing. I'm just going to swap the boards over here, so bear with me while I do that, as I teach you how to write electron configurations using this notation. There's going to be a bit where you need me to stop, I'm sure, where I start going into the D block elements, what we call the transition metals. I expect you to need me to slow down there. Please slow me down if you do. What we've just looked at is that in the quantum mechanic model we show electron configurations a little bit differently. We're starting to understand that the 288 kind of arrangement doesn't work beyond calcium, so it doesn't work beyond number 20. And this year we have to know up to 36, so we have to be able to draw them for that. And what I'm going to quickly go through, this bit of theory you don't need to know too much, is how these are arranged. So if I had my nucleus, my first energy level beyond that, so here's my nucleus, my first energy level beyond that, the electrons basically can be found for most of the time in a spherical orbit. And so that orbit is given the little letter S, and because it's at the first energy level, this is what's called a quantum mechanic model. There is a certain energy that these electrons have. The next lot of electrons have a different quantum amount of energy, so they're found further from the nucleus. But these ones have the quantum value of 1, so they're first energy level. They are in a spherical orbit, which is what the S stands for. I'm not going to say what P and D mean because I've forgotten, to be honest. And it can take a maximum of 2 electrons. I'll just put those in brackets for now. It can take 2. Then beyond that, and it is way beyond that, so this is not to scale, there is another energy level. The first 2 electrons in this can be found in a spherical orbit as well. So it's given that little S. And it can take up to 2. Then it's full. So another orbit, another shaped orbit that looks a bit like dumbbells, so sort of a shape like that. That doesn't mean that they're orbiting like that, by the way. It means it's found for 90-something% of the time, you'll find the electrons somewhere in that shape of cloud, somewhere. Okay, it's not actually going like that. It'll also go through the nucleus, but its shape of cloud looks like that.
Is it kind of like it's
And
going
in
like
3
that?
dimensions. Sorry?
It's kind of like a circle's going like that, so, oh, not really.
No, it's not really like what was described there for the video was sort of like a sausage. It's not quite like that, no. But it's a dumbbell type shape. And that's the p orbital. Because these electrons have the same energy as these ones, it's 2p. And this can take up to 6. There are 3 paths, or areas, sorry. So 3 suborbitals in the p orbital. Okay, there are 3 suborbitals. So that goes back to our what's in common and what's different. We said that they pair up. So each suborbital can take how many electrons? If the p orbital is made up, can take 6, then there are 3 suborbitals. How many does each suborbital take? 2. Good. Sorry, I've shown the numbers there for those that can't see on the video.
I said it.
So that's the way it's arranged. Notice it's 2, 8.
Actually.
So using our old Bohr model way, that tells us that the next lot of electrons
Oh, so the next one is 6p.
are going to be out.
Yes.
Even further, 3s will fill up with its 2, then 3p will fill up with its 6. Okay,
2, 8,
then the next electrons
2,
go to the 4th energy level until we've got 2 of them there. Now here's where things go mental. When we get to scandium, Sc, its next electron doesn't actually go here. It goes back here. So it would be, so we start filling the 3d orbital. Okay, we start filling the 3d orbital. This is why, this 4s2, this is why almost every transition metal has a +2 oxidation state. Because these are the valence electrons that can be most easily removed because of how far away from the nucleus they are and because of all the shielding. So they are really easily removed. This can take up to 10 electrons before we start filling in, I'm sorry, using the colours, that was sort of my way of showing it. We have to fill this before we go to the 4p, which again can have 6. And that would get us to our 36. Is there a question out there?
So when you get to your 5s2,
Yes.
would that elements then fill the 4d?
Yes, it would. So I think it's at trium, I'm not sure, number 39. It would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d1.
Okay.
Yeah, so that would be number 39. I'm sorry, I forgot the name of it off the top of my head. So the way that we draw these is with a little diagram. So let's say, for argument's sake, I was doing carbon. Carbon is number 6, okay? So therefore it's got 6 electrons. First of all, I fill up first energy level with an up arrow or a down arrow, it doesn't matter. And then the down one. This is 1s2, being full. The reason we use arrows going the opposite way is that we say that they are spinning in opposite directions. The only way you could have two negatively charged particles anywhere near each other is basically if they create a magnetic field or something like that that will allow them to get near each other. And if you move a charged particle, you create a magnetic field. So therefore, electrons are charged, they're moving, they're also spinning. So if one's spinning clockwise, one's spinning anti-clockwise, they can get near each other without repelling each other away. So one spins one way, one spins the other. Then we've still got 4 more electrons to go. So now next box, let's fill the 2s orbital. Then in our, sorry I haven't planned this out very well, we've got 3 more boxes to go here because 2p has up to 6 electrons. Each of those is showing a suborbital and how many electrons it's taking. So I write 2p there, and this is the way that I fill it. I fill each suborbital before I start pairing them up. That's the difference between the Bohr model and the quantum mechanic model. Here, we paired those up, but actually these ones are left individual until we've got one there, and then we can start pairing them up.
Is this like easy, like trying to take off, I guess you could say, like remove?
Yeah, it is. I mean, I've picked a bad example. Sorry, I put a 3 there. I picked a bad example of what you just asked, because of course this doesn't make ions. So it makes 4 covalent bonds. And to be honest, that diagram doesn't really help us understand that any better than the Bohr model does. Okay. The reason this becomes important is when we start looking at things that have got things in their 3D. Okay, and this is a thing called Hund's rule, where if all of these are spinning the same way in an orbital, some p orbital, that's more stable than having one paired up and the others unpaired, for example. So the one that I like to use to demonstrate what I'm about to show you is chromium. Okay. Now, chromium is number 24. So, I like to cheat on this, and you're allowed to do this in NCEA. So I'm going to show you how to do that, the shorthand. What we do is we go backwards to find the nearest noble gas. What's the last noble gas before number 24? Argon. So rather than drawing out the entire electron configuration up to argon, I'm going to put argon in square brackets. That means 1s2, 2s2, 2p6, 3s2, 3p6. That's what that means. So we can do that. And yes, you can do that for your exam. So do it, please. Argon. Then, after argon, what's going to fill next? Which orbital? So at the moment, that's got to 3p6 is our last one in there. Okay? 3p6 was our last one. What comes next?
4s2.
4s2, good. So I was hoping my colour coding would help you there. So we're sticking with the black ones at the moment. Okay, so we look at our 4s, and we can put 2 in there. And then that would allow it to be, what fills next?
3D.
3D, okay. And at the moment we're at 20 electrons, argon's 18, so it'd be 3D 4. Okay, I'm just going to open this out to show you what that looks like, and we'll see if there's a more stable way to arrange this. These should all be next to each other. I'm sorry, I've just run out of space. Hopefully this comes up on the screen. Okay, so 4 would be this. 1, 2, 3, 4. Now, there is actually a more stable way to arrange these electrons. This being partially filled is very unstable. Whereas, if one of these electrons was to have a change in its amount of energy and drop a quantum level down to the 3D shell, as it were, I don't like using the word shell, but drop down to here, this is far, far more stable. So now rather than being 4s2, it's actually 4s... How many electrons are in that box? It's 4s1. And it's not 3d4, it's 3d5. Okay, this thing here is called Hund's rule.
So does this only work when there's like one?
Correct. So another one that this works for really well is copper. Copper is 4s1, 3d10. Okay. So one drops from here to completely fill this.
So the whole 4s wouldn't drop off if there was 2 missing?
Correct. You still need something in that 4s orbital to have something in the 3d orbital for an atom. For an ion you don't, but for an atom you do. Okay.
Sorry, why aren't... Is it so that you can fill up all the squares of the 3D5?
No, okay. Hund's rule is about a thing called maximum spin. Notice that the old picture I had, where it had 2 here and 4 here, there was a variety. Some were paired up, some weren't. In this, we're saying all of these electrons are spinning the same way. Whether it's clockwise or anti-clockwise is irrelevant. But they're all spinning the same way. This is a more stable arrangement than having some spinning both ways and some spinning one way. Okay? So it's called, with the phrase we use is maximum spin. So if you can create maximum spin in an orbital, then that's a lot more stable. Okay? And so you've got maximum spin here, it's 1 electron, and you've got maximum spin here, because it's got them in all orbitals, all suborbitals, all spinning the same way. So that's a stable arrangement. That's about the only trick with doing them, to be honest. If you can remember that it goes the black ones, then the green ones, and if you can remember Hund's rule, then you shouldn't have too many difficulties doing the electron configurations for the first 36 elements. Alright, we'll stop there if you can, please.